In this video, we're going to be progressing through Module 14 through pages 506 to 512. And we'll begin by looking on 506 at rate orders. And in this particular section, I'd like you to focus on the exponents in the equations. So in this reaction that we're looking at, we have two of our reactants, nitric acid and the copper 2 hydroxide. And the book describes them. It says it's first order with respect to the HNO3. And so that is sort of a mysterious one there. They don't write a one, but that's what first order means. And then it also says the second order with respect to the copper 2 hydroxide. And so that's where we get this exponent of the 2. And then if you were to calculate the overall order, it would be the 1 plus the 2, or a total of 3. So let's look at example 14.4 on page 506. It says a chemist does a rate analysis of the following reaction, and it has hydrochloric acid plus sodium hydroxide yielding the water plus sodium chloride. It says the experiment reveals that this reaction is first order with respect to each of its reactants. What is the overall rate equation? So we remember for the rate equation, we substitute in the reactants for the A and the B position, and then these have exponents up here because they're both described as first order. They have both 1 as their exponent, but since we don't actually write the 1, it's implied but not actually written out. And so the overall order of this reaction is 1 plus 1, or 2. All right, now let's look at the on your own 14.5, and we have the following reaction, right, is determined to be second order with respect to the phosphorus monoxide, that's this PO, and third order with respect to the bromine gas, that's this reactant here. So our rate equation would have the R equals the K times the PO to the second and the BR to the third. So the overall the overall order is the sum of those exponents, which is just 2 plus 3, or 5. And then the book points out that the orders are not the same as the stoichiometric coefficients, which are here. Right? Rather, they refer to the exponents for the rate equation. All right, another on your own. So it says, 14.6, the following reaction, this is called 1-chloroheptane, C7H15Cl, reacts with sodium fluoride, and it's determined to be first order with respect to the C7H15Cl. So when we put it in the equation here, it's in the brackets, and then there's like that imaginary 1 there. And 0 order with respect to the sodium fluoride. Then as we mentioned before, anything to the 0 power is 1. So that's more or less eliminated from the rate reaction. So in this case, the overall reaction order is just the sum of the 1 plus the 0, or just 1. Okay, so now we go into some calculations on using rate reactions, page 507. We're presented with this chemical reaction. The hydrogen gas plus the iodine is the hydrogen iodide. And if we were to calculate the rate reaction equation, they're given in the book, right? This K and then obviously we're plugging in the two different reactants here. And then if we were to imagine that we're running a reaction with this reaction constant, the K, and then each of the reactants was 0.5 molar, our rate reaction here would be this amount, 0.0015 molarity per second. However, the book would like to point out that after a short period of time, the concentration of each of these reactants is dropping. And so even with just going down to half the molarity for the concentration of the reactants, the reaction rate is significantly impacted. So here it's 0.00019 molarity per second. So you can see the effect of the concentration on your R here. So you can look on page 14.1, figure 14.1 on page 105. You can see here the first few minutes of a reaction, it slows down dramatically. And that is because of the effect that we were just talking about, how this is the same graph we just looked at, how the concentration of the reactants is being reduced, and therefore the rate of the reaction is impacted. So this is an interesting conclusion about the reactants. It says chemical reactions never actually finish. They just keep getting slower and slower until they proceed imperceptibly slowly. Thus, for any chemical reaction, no matter how long you wait, there will always be some reactant left. And that's is shown in this sort of gap here, how there's sort of a lingering amount of reactants that's still present. Surprising, huh? So we can see that there's another factor that also can affect the rate of a reaction, and in addition, the rate constant of a reaction. So we remember that the rate constant is unique for each reaction, but it's also unique for each reaction at a certain temperature. So we know the temperature dependence of reaction rate is determined by the variation of the rate constant with temperature included. Since the rate constant increases dramatically with increasing temperature, the reaction rate does as well. So we know our reactions increase in rate the hotter that they get. So what's interesting though quantitatively is the rate of many chemical reactions doubles for every 10 degrees Celsius increase in temperature. So let's look at an example of that. It says, a chemist performs the following reaction at a temperature of 25 degrees Celsius. So here we have the nitrogen monoxide with the chlorine gas, and here's our product. In an earlier example, we determined its rate equation was this. So we have the R equals this rate constant, and then we have the two orders, the second order, the first order. And then they're given this rate constant at 25 degrees Celsius, and so that's this unit here. And it says, what will be the instantaneous rate of the reaction at 25 if he runs the reaction with both reactants at this concentration, 0.15 molarity? And then, can you contrast that to the rate at 45 degrees Celsius? So, to start off, for the 25, we're just going to plug the numbers into the rate equation. So remember we have the NO here is the, the A. The Cl2 here is our B. We knew the order of them, the 2 and the 1, the exponents here. We're given the K in the reaction up here. basically plug that in here. Everything's multiplied out, and this is your final rate of 0.00051 molarity per second. However, so that's our answer for the 25. Now we need to adjust for 45 degrees Celsius. And in this situation, we know that K doubles for every 10 degrees Celsius. And for this reason, we can take the value that we got at 25, that's on the previous slide, so that's here, and we can multiply it by 2 twice, because as it's going from 25 to 35 it would double, and then 35 to 45 it would double. So we multiply that K that we got by basically by 4, and then solve for K at 45 degrees Celsius. So this was our K at the 25, and then we multiply it 2 times 2, and this would be our answer for the 45 degree. All right, so now let's look at On Your Own 14.7, page 512. It says a chemist runs a chemical reaction at 100 degrees Celsius and determines the instantaneous rate to be at 0.1 molar per second. Sorry, my cats keep wanting to go in and out. She decides to speed up the reaction by running it at 150 degrees Celsius. What is the new reaction rate? So, it's pretty straightforward. We're given the initial reaction rate, and we know that it went up by 50 degrees because it's 150 minus 100. Every time it goes up 10 degrees, we're multiplying it by 2. So it's 2 times 2 times 2 times 2, 5 times, or 2 to the 5th power. And then this is our final answer. The rate that was given us times 2 to the 5th power, and so 3.8 molarity per second. All right, let's look at On Your Own 14.8a. It's a 2-part question. It says, in the On Your Own problem 14.5, you determined that the rate equation for the following reaction, this one that we looked at recently, was this rate equation. So it's to the second order and third order. If a chemist runs this reaction at 30 degrees Celsius with reactant concentrations of 0.2 molar each, and then runs the reaction again at 0 with the same concentrations, what will the reaction rates be in both cases? All right, and then we're given the rate constant at 30 degrees. All right, so at 30 degrees, we're basically just plugging in the information. We have our K here. We're putting it in here. We were given the molarities. So the PO is to the second order, so that's 2 to the second order. This is 2 to the third order for the bromium. And then we multiply it out, and you have this answer here. 4 times 10 to the first, or 40 molarity per second. Now, if we wanted to calculate it at 0, right, we know that it drops by a factor of 2 for every 10 degrees Celsius. So, in this case, it's going down 3 times. So we're dividing by 2 3 times, or also dividing by 2 to the third power. So it's the same R that you got at 30 degrees, and then just divided by 2 to the third. So our final answer here is 5.0 molarity per second. And then there was a B portion of this. And so it says, why do the units in the rate constant, the K, include m to the 4th in the denominator? And so the book sort of explains it from the end backwards. So it says if you know that the final reaction rate is going to be in units of molarity per second, when the overall rate order is m to the fifth, remember because you have 2 plus 3 is 5, when it's multiplied by this rate constant, so this was 1 over the m to the fourth times s, the product then would be in these desired units. So in other words, m to the fifth times 1 over m to the fourth times seconds equals m over seconds. All right, so that is it for this video, and you can look forward to some information on catalysts in our next video.